Hello, I am Artem, and I present type stability in Julia, avoiding performance pathologies in JIT compilation. Julia targets scientific computing applications, so let's look at a typical example. The sum function accepts a vector and a top element. It sums up the vector, except for elements greater than the top. Those get replaced by the top, unless it's the first element. Julia is a dynamic language, so we don't have to put any type annotations here. And we can call sum with arguments of different types. But how does this dynamism play along with performance? A major priority for a scientific computing language. Calling sum with an int vector and an int top works twice as fast as for floating point vector and floating point top. This looks reasonable, and in fact those are examples where Julia JIT compiler is at its best. Whereas the last call with an integer vector and a floating point top comes with surprisingly worse performance. Clearly something went wrong with optimizations here. Let's look closer at what happens with this mixing of types. The inputs to the problematic call are vector of int and a float. These types get propagated to the point where we assign to elm. At this point, the compiler is unsure what type to ascribe to elm. It can be either int or float. This uncertainty propagates further to the addition and then the res variable, making the return type of the whole function uncertain. So, whoever calls sum with these types will likely run into the same kind of problem as we did with the conditional here. It is easy to see that the problem does not arise in the more performant examples, like integer vector and integer top. First takeaway from this experiment suggests that type uncertainty can prevent optimizations. Next, whoever calls sum with these types of arguments may run into similar performance pathology. A Julia developer used to this kind of problem would turn to an utility called code-born type. It prints all intermediate values of the function as well as its body as compiled for the given set of argument types. All values are type annotated, and types are printed either in blue or red. We call blue types concrete. Their representation is entirely clear to the compiler, allowing it to generate optimized code. Examples are ints, floats, or vectors. On the contrary, abstract types are in bold red. Their representation is hidden behind a pointer, which prevents optimizations and leads to performance issues as we saw in the example. In particular, elm and res have the union, float, and int type, which means either of these two concrete types, int or float, can appear at the runtime. More importantly, this also means a boxed value stored behind the pointer on the heap. This will cost allocations. Technical note, we will use color coding with blue as concrete and good and bold red as abstract and bad for the rest of the talk. Trying to abstract away from code-born type output, Julia docs advise to write so-called type-stable code for performance. Informally, this means for all concrete input types in the program, the compiler can infer a concrete return type. Sum is not type stable because of one combination of input types. The compiler detected a union as the result, and unions are abstract types. Notice the for all in the definition. It is sneaky. It doesn't allow us to reason about this property compositionally, meaning a new combination of concrete input types can suddenly render your code unstable under this definition. This reasoning also involves the compiler inference that is not captured formally anywhere. So when setting up our study of type stability, we had to base off of Julia IR, similar to what you saw with code-born type, and leave Julia surface syntax behind. In summary, our goal was to connect type stability to optimizations. To that end, we model Julia's IR and its JIT. Again, IR not the surface syntax. We come up with a missing piece in Julia vocabulary and introduce type groundedness, which just as stability speaks about abstract and concrete types, but is stronger. It is groundedness that programmers should strive for to get the best performance. We connect the two notions, stability and groundedness, to devirtualization, the key optimization in Julia, as we learned from the previous work. Devirtualization is important because first it removes dynamically dispatched calls that are all over the place in the Julia's non-optimized semantics, and second, it unlocks other optimizations like unboxing and inlining. Lastly, we submit the corpus analysis detecting how much type stability and groundedness is in real Julia packages. I will not go into details of our formalism called Jules. Instead, I introduce it to you with several examples that provide intuition for all key results. The syntax of Jules is an SSA-like IR, akin to what we saw earlier with code-worn type. This allows us to reason about concrete and abstract types of sub-expressions. Jules has a baseline dispatch semantics and an optimizing JIT. The JIT has two tasks. First, specialization of methods to concrete argument types at call sites. It produces what we and Julia call method instances. Those are added to a method table that's a part of a program state. Second task is to apply devirtualization in the specialized instances. To describe devirtualization, Jules has two kinds of method calls, dispatched and direct ones. Notice the syntax. The bang and types of arguments distinguish direct calls from dispatched ones. As devirtualization is our main goal, the distinction will play a role. Now let's look closer at the two tasks the JIT performs. Imagine a program that gets to a dispatched call to f with these arguments. In the base semantics, we would dispatch to the first entry in the method table with the two methods. In the JIT semantics, we would first ask the JIT to take this generic version of f and generate a version of it specialized for int and float. JIT would update the method table, not touching the program, and we will step into the specialized version. But what does this new version look like? As we said before, our JIT performs only one optimization, which is devirtualization. Let's say we are compiling f for arguments of concrete types t0 and t1. The first step is to run type inference on f's body with those argument types. This will produce a typing for each slot in the function. Next, JIT will employ the inference result to devirtualize as many calls as possible. In the example, JIT replaced the dispatched call to G with a direct call, a successful devirtualization. It was possible because type inference was able to deduce concrete types for all arguments of G, %1 and %0. During this process, JIT had to recursively instantiate G with T0 and T1 and update the method table accordingly. On the other hand, the dispatch to H wasn't resolved because the type of its first argument, %2, was inferred as any, which is an abstract type. Assume in our running example we had all types concrete as the result of type inference. In that case, we would have no dispatches at all. We call this full devirtualization of a method instance. That's the most desired state for any instance, and this prompts the definition of type groundedness of an instance. All the slots are inferred with concrete types. We prove that whenever a method instance is grounded, our JIT can fully devirtualize it, leaving no dispatch behind. Now let's turn to the role of type stability, which is closely related to groundedness. Initially, in the first example, we failed to devirtualize H because of an abstract argument. A reminder, we only devirtualize calls for which we know concrete types of all arguments. How did it happen that H had its first argument abstract? The value comes from the slot %2, which holds the result of the call to G. We conclude that the type inference on G with concrete types T0 and T1 on the input detects any as the return type. If a function given a set of concrete inputs cannot be inferred to return a concrete type, that's what we call type unstable. This is the case with G. Just like with sum in the introduction, which when called with vector int and a float, was inferred to return a union. We prove that a grounded instance can only call stable ones. This establishes a relationship between the two properties. Note that it's not sufficient to call stable instances to be grounded, but only necessary. The reason is, you can use a conditional to break your own groundedness. That's exactly what SUMFunction did. To recap, using Jules, our model of Julia JIT, we introduced two formal notions relating types and optimizations. A type-stable instance may not run fast because its internals can be abstract, but it does allow its callers to run fast, in the sense that if some instance relies only on type-stable calls, it can become grounded, and in that case we are able to fully devirtualize it. Lastly, we emphasize that the properties and therefore possible optimizations rely essentially on the power of type inference, which the programmer has no control over. It's hard to build intuition about this component of the system, and in the paper we list a number of high-level requirements to it, under which all our results will hold. In our dynamic analysis, we run test suites of 1000 of most popular Julia packages. Results show high numbers for both type stability and groundedness. In many packages, we see that the vast majority of methods are small and grounded. We saw several patterns for type-stable methods. First, if you always return either true or false like a predicate, you'll qualify as type-stable. Secondly, many type-stable methods resemble familiar polymorphic algorithms like map or filter. At times they would have some additional side effect in code, like logging or caching. More of those patterns, with real-world examples, can be found in the paper. The code and data we used in analysis are available in the artifact. To conclude, let me say that type stability is an odd property. First, it's a whole program property. Stability of a method depends on which argument types the method is called with. Designing a static and precise type stability checker for a type annotation language as rich as Julia's would be a challenge. Second, precise reasoning about stability and groundedness happens only at the IR level and involves the JIT compiler. We hope that our work will help Julia programmers build a mental model of the two properties and understand where the performance of their code is coming from. With this model, the compiler should not seem like a black box that can magically optimize any user-defined code, and the programmer can help the compiler to do its best. You can see the summary of the work on this slide. More details about formalism and dynamic analysis can be found in the paper, and the artifact is available. Thank you.